Properties of carboxylic acids. Carboxylic acids with low molecular weight are liquids at room temperature and have characteristically sharp or unpleasant odors. And you know that if you've ever been around vinegar, acetic acid, it only has two carbons in it, right? So it's a low molar mass and it has a very pungent odor that stings your nose. Heavier carboxylic acid, so if you have more than 10 carbons, they become wax-like solids, okay? And then stearic acid, for example, which has 18 carbons in it, stearic acid, is mixed with paraffin to produce a wax that's used to make candles. And so if you take a look here, if we go from formic acid, which has one carbon in it, to acetic acid, which has two carbons, then we have butyric acid, which has four carbons, valeric acid has five carbons, caproic acid has Caproic acid has six carbons. Then we have 12 in lauric acid. Then we have 14 in myristic. In palmitic, we have 16 carbons. Then we go up to stearic acid, which has our 18 carbons. You can see here that the melting points, generally speaking, the melting points increase. So melting point, we can see here that the boiling points increase steadily until we get up to the myristic acid in which it decomposes before it boils. But the reason why the small carboxylic acids have lower boiling points is because they have shorter chains, and so there's not going to be as much London forces experienced between these the chains, the hydrocarbon chains. Anyhow, and then you can see the solubility of low molar mass carboxylic acids like formic acid, acetic acid, butyric acid is infinite. They have an infinite solubility in water, which is also defined as miscible. But if you go to valeric acid and caproic acid, you can see the solubility starts to go down until we get into those wax-like carboxylic acids, right, where we have, 12 carbons and more, and those are insoluble in water. And again, the boiling points of carboxylic acids, as you saw, are very high. I mean, if we go back to the previous slide, you see that the boiling point of formic acid is higher than that of water. And so the carboxylic acids have higher boiling points than any other functional group that we've looked at so far. Now, for simple non-aromatic compounds, the boiling points usually increase in the following order. So we go hydrocarbons and ethers, the lowest boiling points, followed by aldehydes and ketones, then followed by aldehydes, and then carboxylic acid. So you can see here on this graph, you can see when it comes to boiling points, carboxylic acids are this line at the top, and so they're the kings of the castle. That as molecular weight increases, all of the boiling points go up, right? As you increase the molar mass, it doesn't matter whether it's an alkane or an aldehyde or ketone or an alcohol or a carboxylic acid, right? They all increase as the number of carbons increase. But again, you can see that if you compare the four of them, right, alkanes have the lowest boiling points, followed by aldehydes and ketones, which are higher. Then primary alcohols and carboxylic acids, like I said, are the kings of the castle. And one of the reasons why carboxylic acids have such high boiling points is their ability to form what we call a dimer that's shown here, where you can see hydrogen bonding is occurring between the the carbonyl oxygen rather, and the hydrogen of a carboxylic acid. And it can also occur with another molecule of another carboxylic acid. So you see here, this is a carboxylic acid right here, and this is a carboxylic acid here. And these dashed lines that I have highlighted in yellow, those are the hydrogen bonds. And so hydrogen bonding is very maximized between carboxylic acids, resulting in their very high boiling points you see here at the top of the graph. Now, a little more about water solubility of carboxylic acid. So, as I was saying, low molecular weight carboxylic acids like acetic acid or propanoic acid are very soluble in water. Why? Because the hydrogen bonds formed between the carboxyl group and the water molecules enable them to dissolve in water, right? Like dissolves like, because, right, in our carboxylic acid, we have the polar portion that comes from the carboxyl group, okay? So, this would be our polar portion, right? And then the R group, whatever is on this end, is going to be nonpolar. So if the nonpolar part is small, then it's going to be a low molecular weight carboxylic acid and it will be soluble in water. But just like we saw with aldehydes and ketones, the water solubility of carboxylic acids goes down as the length of the nonpolar hydrocarbon portion, the R group, gets bigger. So as this portion here gets bigger and bigger and bigger, the carboxylic acids become less and less soluble in water. So if we have a carboxylic acid that has 8 or more carbon atoms, it's not going to be soluble in water, okay? And it's going to be considered to be insoluble. And we saw that on the previous slide. So organic compounds may generally be arranged according to increasing water solubility in the following order. So hydrocarbons are the least soluble, then we go to ethers, then aldehydes and ketones, then alcohols and carboxylic acids are the most water soluble of all these different functional groups. And because forces resulting from hydrogen bonding play important roles in determining both boiling points and water solubility, it should not be surprising that the same order is generally observed for these two properties. So we saw that boiling points and water solubility have similar trends, and that the carboxylic acids are at the top with alcohols and the hydrocarbons are down at the bottom. Now, in most chemistry classes, we cover acids and bases, and you should know strong acids. I'm sure you've all heard of sulfuric acid, which is a strong acid, or hydrochloric acid. Well, a carboxylic acid is an acid, meaning it is an H plus ion donor, okay? But they're weak acids, so keep that in mind. A carboxylic acid is not a strong acid, right? Think about it. If you pour vinegar on your skin, it's not going to burn your skin. It's still an acid, but it's not a strong acid. So carboxylic acids generally behave as what? They are weak acids in water. So the proton may leave the acid, converting it into a carboxylate. So we see the acidic proton on our carboxylic acid here gets donated to the water molecule to give us a hydronium ion. And so we're left over with a carboxylate. So we see that if we put acetic acid in water, that it actually does lose some of the acidic protons to give you hydronium and the acetate ion here. The amount of dissociation here is about 5%. So 5 out of every 100 acetic acid molecules is going to dissociate to give you an acetate ion and a, what's this called? Hydronium, right? A hydronium ion, H3O plus. Now again, although they are weak, carboxylic acids will react readily with a strong base like sodium hydroxide or potassium hydroxide or lithium hydroxide to form salts. So if you take a carboxylic acid, here's the acidic proton, again highlighted in yellow. If you treat that with a strong base like sodium hydroxide, so remember, sodium hydroxide is a very strong base, okay? It's going to rip that hydrogen, that proton off like nothing to make your carboxylate salt. And here's a specific example. If we take acetic acid, we treat it with sodium hydroxide. The hydroxide and the H plus ion from the acetic acid combine again to make water, as we saw in the previous example. And the salt that we get is sodium acetate. All right, cellular respiration is the process by which humans utilize oxygen to produce adenosine triphosphate, or ATP, which is energy. A byproduct of this process is carbonic acid, which reacts with water and in turn helps regulate oxygen levels in the blood. And so our question is, predict the products of a reaction of carbonic acid and water. And so what's going to happen is, since carbonic acid is an acid, it's going to give up one of its acidic protons. You see there's two of them, but it's only going to give up one. And so we're going to end up with our hydronium ion, of course, because once water takes on H plus, we get H3O plus. But what's left over is going to be everything else. So we're going to have our carboxylate salt. So this would be a bicarbonate ion. So this is the bicarbonate ion. And of course, we end up with a hydronium ion. So those would be the products of the reaction between carbonic acid, which is the formula for carbonic acid is H2CO3. So the reaction, the products of the reaction between carbonic acid and water.